sent a supplemental lecture notes to you this morning, so I hope you have received it. Okay, and so because our textbook is very basic, it's a textbook written by Krasik. This is a wonderful book, versatile, comprehensive. Okay, but because it is comprehensive for engineering, mathematics, so so I have to write some supplemental material for almost all sections that I will teach in this course. And as you know, this course is on partial differential equations and the complex variables. And so as I have stated in my syllabus that this semester will comprise of two parts. First part is about partial differential equations, how to solve it. And the second half of the semester will about complex variables, especially complex functions and many useful mathematical operations on complex functions. Okay. And for the first semester, the first half, that the basic tool to solve, in this course, okay, for partial differential equation, we will use Fourier analysis. So I try my best to give you a comprehensive treatment of Fourier analysis. As I know that some of you may encounter, as EE major students, you have to check the core signal systems. In this course, that the very basic tool will be Fourier analysis. But in that course, you will learn how to apply, even though you have to learn the basic concept, but the most important is how to apply Fourier analysis to many mathematical and engineering problems. So I have decided to, in this course, to give you a very basic theory of Fourier analysis as possible as I can. Yeah. So you will see that in each section, maybe, for example, in the first section, I have write 13 pages. Okay, so that, but as you know, we have a very short time. Even though we have 18 weeks semesters, but it's still for me to cover. Just half of the semester to cover partial differential equations is sometimes is a kind of mission impossible. But I've tried my best, And so one of the purpose for me to write the lecture notes is that maybe in the lectures, if the time is limited, then I will skip some of the detail of the proofs of all the theorem. But the logical structures of the theory will be given in my lecture notes. Okay, as you will see. And of course, you are welcome to interrupt me. All right? If you have any question, it's very important to raise your question timely. Don't. Of course, if you understand everything, that's no problem. That I would be glad to see that. But if you have any question, just raise your hand. We can have a very short or brief discussion. Okay, and of course you can, as you know, we will tap my lectures and send the videos into my YouTube channel. So of course you can review all the materials or the lectures delivered in the classroom. Okay, so I think you have videos and you have hangouts, have textbook. So I believe you will have everything you need. Okay, and so the only thing is how much time you will invest in this class. Okay, if you invest enough time, I believe you will have a good performance. And as I have described in my syllabus, basically you will have a quiz every week. So you have to prepare for the quiz every week, okay? And I will assign homework, just recommended homework for you, all right? And that would be a very good starting point to prepare for quizzes. Okay, all right. And we have 2 midterm examinations and 1 final examination. And the coverage of the final examination will be every material taught in this semester. Okay? So you have to understand, okay? The whole semester will be covered in the final examination. Yeah. All right. So do you have any questions? Yes, please. Yeah, in the EE system, I think. Yeah, because I'm like new here, so I don't know how to into that. No, I entered, but I've heard in another course they wanted to use something else that I don't know. No. Yeah, because we haven't yet stabilized the student list. Okay, so. The university information system is the most updated student list that I can have. Yeah, faster than the EE learning system. E-class, I'm sorry. Yeah, just a summer vacation. I forgot a lot of things. Yeah, so yeah, but I will put everything in the E-class. E-class, okay, yeah, okay, no problem, yeah. So, but if you have any questions, you're welcome to email me. I think you know my email. If you don't know, go to the E department homepage. Okay. Other questions? Okay, so if you don't have right now. So I will start my lecture. All right. All right, so the sequence of the chapter will follow the textbook. All right. Okay, so in the theory of Fourier analysis, the first topic should be so-called Fourier series. All right, and so a function f defined on the set of all real numbers R is called a periodic function. All right, so if there exists a P which is positive, all right, we call a period of F such that f of x plus P is equal to f of x for all x in the domain. Okay, so that and by the way, I have to specify the range of the codomain of this function, right? Because I just say that it is a function defined on the set of all real numbers. So we know the domain of this function is R. So what is the codomain of this function? All right. implicitly, in here, it can be real valued or complex valued. All right? Or maybe a set of, just a set. Okay? So the value of function can be alphabetical value, anything. Be anything, okay? So not specific to real value or complex, but of course in Fourier analysis we will deal with either real valued or complex valued function. Okay. All right, so such kind of a detail. If you have any question, you can just raise your hand, and I will give you a very short answer. All right, so it is good for communication between me and you. Okay, right? Yes, please. Yeah. You mean if they well, but this is an English teach class. Thank you for your kindness. But if you want to raise your question, you can use English or Mandarin, Chinese, as I said in my syllabus. But if you use French, maybe I will invite a translator here. Okay. Or someone can be my translator to translate French to English. That would be good for me. Thank you. I know, but I have to teach in English. Because I choose. This is the English teaching class. Yeah. Okay, good. Now, so you know a period, right? So when I say a period means that this function may have many periods. But they would have a smallest period. Okay, so it's called the fundamental period. Okay, fundamental period, or just period. So the period of when we use it means that the smallest one. Okay, and of course you have to prove that. But I think you have the experience this in high school, I believe. Okay, I believe. All right. So for any periodic function, all right, it must have the smallest period satisfy this one, and the other period will be integral multiple of the smallest period. Okay, so that is a property of periodic functions. Yes, please.
Every other function is a multiple of the smallest fundamental function?
Yes. Yeah. So you can do, if you want to prove that, you can prove by contradiction. Yeah. Okay. Think about that. That would be a very good, an interesting problem for you, to show that every periodic function has the smallest period, and every period of this periodic function would be a multiple, integral multiple of this smallest period. Yeah. Okay. All right. All right, so many functions are periodic functions. For example, the sine function, or cosine function, okay, and a function defined in this way, Okay. I cannot just write tangent function. The reason is that tangent function has a domain which is not equal to R. Why? Because it's not defined. Tangent function is not defined at this discrete point. And I say I will focus on function defined on the whole real lines. Okay, so I have to amend this function. So I put zeros deliberately to every point where the tangent function does not, the main function is not defined. Okay. Okay, so you have many other things. So the period, all right, for sine function, okay, can be 2 pi, 4 pi, 6 pi, many, right? And the 2 pi is the smallest one, okay? Similarly, for this one. But for this function, the smallest period will be pi for tangent plus zeros for the point where tangent function is not defined. Okay, 2 pi, etc. Okay, so these are familiar examples for you. Okay, so they are periodic functions. Okay, so now so I will give the first theorem. Also go nullity of, right, so they are, and so they are maybe I'll say here. So this called trigonometric right? So trigonometric functions are linear functions we have. And so they have some good properties. So okay, sorry. Before I state, so that observe that. Okay, 1 cosine x sine x and the cosine to x and to x sine n x or periodic okay, and so I think I have to, I forgot to put a non-constant Okay. I'm sorry, I forgot to put non-constant because for constant functions, we don't have the smallest period. Sorry. Okay, but constant function is a special example of periodic function. Why? Because any p greater than 0 will be a period of a constant function. Right? Okay, so now, constant function 1, cosine x, sine x, cosine 2x, sine 2x, and cosine nx, sine nx, etc. are periodic functions. Okay, with the same period, 2 pi. Okay, and so which form the so-called trigonometric system. Okay. Okay, so it is a set of periodic functions. Okay, and it's an infinite set. Okay, so if so it comprises of infinitely many periodic functions, and you can find a common period 2 pi. Okay, 2 pi there. So even though the period, I mean the fundamental period of cosine 2x is pi, right? It is pi. Okay, but 2 pi is still a period of this function. Okay, so we can say that this system, all right, has the same period 2 pi, and we call this is a trigonometric systems, right? And a property of the trigonometric system is orthogonality. Okay, so all right. So the statement is here. The functions in the trigonometric system are orthogonal over this closed interval. So this closed interval composed of a period of these functions. Okay? Because the length of this period is 2 pi. Okay, and we call them, it will be here. So orthogonality is described in here. First of all, the integral of the cosine, the two sinusoidal functions, okay, is 0 for all n greater than 1. So except the constant function 1, right? Except 1. If you integrate constant 1 over this interval, the value will be 2 pi, which is not 0. Okay, but other than the constant functions, okay, all this trigonometric function, this sinusoidal function, has the definite integral, which is equal to 0. Okay. The second is that, okay, so here comes the orthogonality. The cosine n of x times the cosine m of x So if you multiple two cosine functions here, n is not equal to m. All right, so this product, and you integrate over this interval, the value is 0. So it is the same if we replace the cosine function by sine function. Which is 0 for O and M greater than or equal to 1, and n not equal to m. The third one, if the integrand is the multiple of a cosine function and a sine function, right? Then this integral would be 0, okay, for all n m greater than or equal to 1. And here, n can be equal to m, okay? It can be equal to m. All right. And so the proof, I just say, you should know this in calculus. So let me have a poll. If you don't know any of these three, please raise your hand. Don't be shy. I know. Okay. So that's good news. Okay, thank you. All right. So so you know the proof, because the proof used in calculus can be completed, just as I say, by applying sum and difference identities. All right, in right? So in trigonometry, okay. Okay. So this one can be obtained by using the antiderivatives, right, of cosine function and sine function. Okay, you know the antiderivative of cosine function is sine, right, and the antiderivative of sine function is cosine. So now, okay, so you will have this one. The first one is very simple, just by using antiderivative, and the second and third one is by using the sum and difference identities in trigonometry. Okay, you have learned, maybe date back to your senior high school. Okay, because for me, we have learned these identities in junior high school, and then apply the one, right? And apply one. Okay, so if you forgot how to prove it, go back to see your calculus textbook. Okay. All right. So now I will introduce a trigonometric series. Is here a0 plus a1 cosine x plus b1 sine x plus a2 cosine 2x plus b2 sine 2x plus plus an cosine nx plus bn sine nx plus . Okay, and we can use a concise notation. An cosine nx plus b sub n sin nx. Okay, so here, where A0, A1, B1, A2, B2, etc. are constants. Okay, we call coefficients of trigonometric series. Okay, so all these coefficients are constants. All right, and so such a trigonometric series will be a periodic function. Okay, with a period 2 pi. Okay, if the series converges, okay, for all x in R. Okay, because only when the series converges for all x in R, it will define a function. Okay, it will define a function for all x in R. Okay. And we say that with a period 2 pi, because the fundamental period, right, cannot be seen, right, from such a generic term. For example, if all the A0, A1, and B1 are zeros, A2 is 1, B2, etc., all these are zeros, then this trigonometric series is just cosine 2x, right? And the fundamental period of this function is pi. Okay? So as you know, that the fundamental period can be determined only you know what are these constants. All right. So now, a natural question here. Okay. Can a periodic function f with a period 2 pi be expressed as a trigonometric series, i.e. such a function can be written for all x in R for some A0, A1, B1, AN, BN, So that would be a question. Okay. So this is a main question in Fourier series. Yes, please.
For the constants,
Yep.
they have to be defined. Like you have to know.
Yep. So we have to know. So if the answer is yes, if it's yes, then we have to find out the way to calculate all these constants.
So, wait, sorry again. There are cases where they are defined, so you already know the constants, or they're...
You don't know. So the question can be there are many possibilities to answer the question. It could be that some of the periodic function cannot be expressed, okay, like this one. Means that we can't find some constants. Yeah, we can't find. And maybe some of those periodic functions with a period 2 pi can be expressed in this way. All right? And so if the answer is positive, you have to find a method to calculate all these constants from the original function f of x. Yeah, right? So it's, and okay, so I think from your experience that you can find some function which can be expressed by a trigonometric series. For example, the functions in these systems, any of them, right, can be. For example, cosine x. For cosine, if f of x is cosine x, then it's very easy. A0 is 0, A1 is 1, B1 is 0, and all a sub n are zeros when n greater than equal to 2. So you know, right? So you know they are, this is a simple answer to know that all these functions in the trigonometric systems, they indeed, right? But some of the periodic functions, for example, in electrical engineering, a lot of signals, no matter it's a voltage signal or current signals, many of these signals, for example, clock signals, okay? Clock signals are periodic signals, and can clock signal be expressed as a trigonometric series if the period of the clock signal is 2 pi, of course. But as you know, we can scale, right? We can do the time scaling to make any clock signal to be a periodic function with a period 2 pi. Okay. Okay, so and in our world, in the physical world, there are a lot of phenomena can be modeled by periodic signals or periodic functions. Okay, so it's quite natural to know that for a periodic function, some specific periodic function, can we really express this function to be a trigonometric series? Okay. Okay. Other questions? No. Good. All right. So to answer these questions, we have to derive some necessary condition if the answer is positive. Okay. So because okay. So in logic, right? This is logic. So if the function, if the answer to this question is positive, then we try to find some necessary conditions. So that means that if a function cannot satisfy these necessary conditions, then for such a function, the answer is no. Okay, so that is one way to give a partial answer. All right. All right. So all right. So to answer this question. All right, these conditions for the positive answer. Okay. So we derive some necessary conditions. And right. So okay, we will not go into this, but for some questions, if we find necessary conditions, and we can justify that any periodic function cannot satisfy some specific necessary condition, then the answer should be no. Okay, firmly, no, firmly, right? But this is not the case, right? In our theory. Okay, so assume that the answer is positive. All right, so assume that f of x can be written, okay, as here. Okay, for almost all almost all x in R. Okay, so assume almost all. We just loosen our requirement, okay? Almost all. Almost all is not equal to all, okay? So, for example, in a famous for Clark, okay, and this is minus pi, minus 2 pi, pi, 2 pi, 3 pi, etc. 1, minus 1. So this is a periodic function. Yeah, this is a periodic function. And with a period 2 pi. Okay. Then it is, we will see that we can find, I mean, at the end of this, at least in this, at the end of this section, we will find that the series, okay, this periodic function, because it has discontinuity, okay, at the multiple of pi, okay, you have discontinuity. You can see that because it has jump, right? So so we count so that this trigonometric series cannot converge, all right, into the points here. Okay, maybe, all right. And but not equal to. So this one may converge to some point, but may not equal to. So we will see as a function. I have to specify. So for example, I choose left continuity. So okay. So a solid data means that the function, okay, at when x equal to minus pi, the value is positive 1, not minus 1. Okay, it's positive 1. Okay, so now this function is well defined. Okay, in the whole real line. in the whole real line here. Okay, and for the multiple of 2 pi, the multiple of pi, maybe this trigonometric series converge, but the value of this series may not be equal to the value we assign here. Okay, so they are not equal. So they are not equal at the multiple of pi. All right, so they are not equal for all x in R, but they are equal for almost all y, except the point, and the length of this point is equal to 0. Okay, so now I will explain what is the meaning of almost all. Okay, so i.e. the partial sum function x sub m of x is 0 plus okay. So this is indeed a function because this is just a sum of a finite many sinusoidal functions plus constant, right? So this is indeed a function. And this function should be continuous and have all order of derivatives, okay? Because sinusoidal function has all order of derivatives, okay? So they are very smooth functions, all right? So these partial sum functions are very smooth, okay? So the partial sum function converge to f of x as m goes to infinity. So goes to infinity for almost or for all x in R, except x in some set. Okay? Such that the length of delta is 0. Okay. Okay, so delta is a subset of R. Just like here, delta is equal to m pi. Okay? So delta is just the set of all integral multiple of pi. And it consists of infinitely many points, but countable, right? You can count them. So the total length of this set, so the length is 0. Okay? The length is 0. Okay? Because the point is discrete, right? And the length of each point is 0. So if you add countably many 0 together, the value is 0. Okay. All right. Okay. So almost all. The meaning of almost all is here. Okay. So that this partial sum function will converge to f of x. All right. For all x except the x is in a subset. And this subset has length, okay, which is 0. So that is the meaning of almost all. Okay. Okay, and so of course, if we have a strong version, means that f of x is equal to this trigonometric series. All right, for all x, that is much stronger than the statement here for almost all. Right. So if the delta function is the empty set, then of course almost all becomes all. Okay, so if this subset delta is the empty set, okay, then it becomes true all. Okay, so I have clarified the concept of almost all, right, in my explanation. So any questions? Okay, thank you. And we further assume one, if we define a function converges for almost all, okay? So you can see that the series, all right, the series has positive terms. So you can see I take the absolute value function. So they are all positive. So if you have positive terms in a series, then this series either converge to a finite positive non-negative number or go to infinity. Means that diverge to infinity. Okay. Sometimes we call it converge to infinity, but in calculus, when we say converge, we mean that the value, it converges to a finite value. Okay. But as we know, that because they are all positive, so if it doesn't converge, it means that the value becomes to infinite. Okay, come to infinite. So we say that the g of x function converge for almost all means that it allow that a subset of subset delta such that for those x in this delta, all right, and the length of delta is 0, this series will diverge to infinity. Okay. Okay. So, but except for that, all other points, this series will converge to a finite number. Okay. So that is the meaning. Converge for almost all. The second thing is that the integral. Okay. Of course, this function, all right, when we have the integral from minus pi to pi, the integral is finite. Okay. Right. So So if we have two conditions. Okay, so now we can say, a sufficient condition for 1 and 2 to be true is that the series sum of the absolute value of the constant coefficients, okay, is finite. So if this series converges. The reason is that the cosine function and sine function, so as we know, for this one, okay, so the reason is that the cosine function and sine function are bounded by 1, right? So the absolute value of cosine function or sine function are bounded by 1. Okay, so that the series sum would be, and so if this one is finite, then this series will converge for all x, for all. So this is a simple but strong sufficient condition to guarantee that 1 and 2. Okay. And so the integral must be finite, because that in this case, g of x has upper bound, which is equal to this series sum. Okay, so it has an upper bound, and an upper bound integral over this definite interval, then this integral has a value which is finite. Again, any questions? So in this case, I used and so that here would be okay. So here, so if this is true, then we know g of x. Okay, so this is series converged for every x, and the value is less than this constant. Okay, and so this implies that the integral here has upper bound, which is constant, which is finite too. Okay, so any questions? Okay, so let's take a short break up to 2:30. Okay. OK，哦好，OK。 Okay, so our next target would be deriving some necessary conditions. Okay. All right. So now, so we have the partial sum function. So A0 plus the summation okay. So the partial sum function here. So when we take the absolute value here, take S value here. So now the absolute value of this finite sum would less than equal to the sum of absolute value of each term. Okay. So that is the situation here. This is too big. Let me use the smaller one. Okay, and so this is bound, upper bound for all m equal to 1 and for x to r. Okay, and I think I have to stress we have, of course, we have assumed that okay. So so this is implicit required that the g of x is a non-negative function. Okay. Or so I think of course this is non-negative. So I say so the upper bound maybe I would say that for almost or okay. So that would be sufficient, just for almost all in R. Okay. Okay, and by I'll stay here, the dominated converting theorem okay. So the dominated converging theorem, I have said a theorem in my lecture notes is long. So I don't want to stay here. So I give you the reason that that our target is here, right? This is our target. So we have give a positive answer that we assume that this is true. Okay? So we assume that this is true. This is true. Okay, and okay, so we assume this is true for almost all x in R. Okay, and we assume that g of x, because g of x is very close to f of x, except that the term we used is the absolute term, the absolute value of each term in here. Okay. So that this function is converge, also converge. Okay, and we know that the g of x itself has finite definite integral over the interval from minus pi to pi. Okay, so we have assumed 1 and 2 and 3. You can say these two additional conditions, right? So we have 1, 2, 3 conditions. And if we have these 3 conditions, okay, so by the dominated convergence theorem, right, so f is absolutely integrable over this interval. Absolutely integrable means that if you integrate the absolute value of the function f of x over this interval from minus pi to pi, okay, the value is finite. Okay, it's called absolutely integrable. Okay. And the theorem, the dominated convergence theorem, is a big theorem in in analysis. Okay, so if you want to really, I state the theorem in my lecture notes, but to have a proof, you have to go to advanced calculus. Okay, but I think not all of you have this background. So I just use this theorem here, okay? And so it gives us this result. That that means that if this is true, for almost all x in the real line, plus these 2 conditions, then we know this fact that the function f of x itself is absolutely integrable. Okay, so it gives me, and the other thing, important thing, and we have the integral of f of x, okay, right, as we know, okay, so we know f of x is obtained by the partial sum, right? So the partial sum will converge to f of x as m goes to infinity, all right, for almost all x, right? So that f of x and this limit, all right, they may be, this limit may not converge, or if they converge, but may not equal to f of x for all points in a subset delta. And this subset delta has length 0. Okay, just like here. And so if we take an integral, because for a point, the differential is 0, the differential length is 0, so that their integral will be the same. Okay? So I will create a window here. If f of x equal to g of x for almost all x in R, almost all in define an interval I, and exist, then, all right, so if we have two real value or complex function, all right, so they are equal for almost all x, sorry, in an interval. The interval can be finite interval like from minus pi to pi, or semi-infinite from 0 to infinity, or the whole real line, arbitrary. Okay? So I just say interval. If they are equal for almost all x in the interval, and we know one of them, for example, f of x, right, this integral exists, right? Then the other integral exists and must be the same. Okay, so this is a factor from analysis that once two functions, okay, even though they are disagreed in a set, in a subset of R, but if the length of this subset, like a delta, is 0, all right, and if one of them has a finite integral, is integrable, then the other one is also integrable, and the integral will be the same. Okay, so this is a fact. Okay, all right. So I use the fact to say here, because these two functions, the limit of this function, as we know, it will converge. Okay, to f of x for almost all x here. Okay, and so that this is from that f of x is the value okay, of this limit for almost all x. Okay, and the important thing is that the dominated convergence theorem gives us this identity. What? We can move the limit out of the integral. Okay. Okay. It's not always true that we can move the limit out of the integral sign. Okay? It's not always true. But by dominated convergence theorem, this is true, which says that if in addition we have these two, if we have this one, and this function is called the dominated function, right? Because f of x will be dominated by g of x, because this is the absolute value. Okay, and this dominated function has finite integral. Okay. So that's the reason why it's called dominated convergence theorem, because we have the dominated function. We find one. Okay, so this one is dominated. Okay, and so that once we exchange the limiting process with the integration process, then things becomes to be easy. As we will see here, Okay, so that now and this is a partial sum function, right? So we see that there are only finite many terms here. Finite many terms here. So if we take the integral of this partial sum function, it becomes to the sum of the integral of each term. Okay, because definite integral has linearity property from calculus. Okay, so we have A0 plus okay. All right, so the integral of this continuous function, this partial sum function, is equal to this sum. And from the orthogonality of the trigonometric system, we know that the integral of cosine function is 0, integral of sine function is 0. Okay, so that this integral is 0. And so that we have 2 pi. So this one is 2 pi A0. Okay, so we have the limit m goes to infinity and the 2 pi A0. And this is a constant independent of m. Okay, so that the integral of this function, we know the value, which is just 2 pi A0. All right, so this is by theorem 11.1.1, okay, from here, from this theorem. So that means that we can, if this is true, then A0 can be found. So from here, so that A0 is 1 over 2 pi. Okay. So if the answer is true, so if the answer is positive, then A0, right, plus 2 additional property here, right? So the answer is true, and we assume we have these 2 further properties, okay? These 2 further properties, and these 2 properties, in many situations, it's easy to check, okay? They are easy to check. So if then we know how to find A0, the constant. So the constant is just 1 over 2 pi times this integral. And the existence of this integral is because of the dominant convergence theorem. Because if a function is absolutely integrable, then this function is integrable. Okay? This is from calculus. Right. Right. So if a function, if the absolute value of a function has finite integral, right, then the function itself, without the absolute sign, the function itself is also has definite integral. Okay. So absolutely integrability is stronger than integrability, okay, as we see from calculus. So, okay, so that this integral exists, all right, because of the dominant convergence theorem, okay, and also due to these 2 properties here, okay, so that we know how to find A0, okay. Okay, and so we follow the same line of thinking. We can find constant an and bn as follows. Okay, so for k greater than or equal to 1. Okay, so let's see. we check f of x times cosine kx. All right, so we find this one. And we check this integral. This integral must exist. Why? Because that this product, f of x, all right, so that we can, this product is absolutely integrable. Why? Because that, let's say, okay, now here, right, I evaluate the integral of this integral, which is the after value of this product. As we know, because the after value of cosine function is less than or equal to 1, so it is upper bounded by this one. But once again, it's finite, right? So that this product is absolutely integrable. And so it is integrable. So this integral is finite, exists and finite. Okay, and so here, so this is becomes to the limit, and m goes to infinity, Sm of x, and the cosine k of x, and d of x. Okay, and again, that by the same reason, the dominated convergence theorem, okay, the limit and the integration is exchangeable. Okay. So once again, so that we can exchange the limit and the integration because of the dominated convergence theorem again. Okay. So once we lift out the limiting process, now things becomes too easier as we have done before. Okay. So this is the limit. Okay. And plus okay, so a little bit crowded here. All right, so now here, because k is greater than or equal to 1, so by this theorem, part 1, all right, so this term is equal to 0. Okay, and when we look at here, the product here, n and k. If n is not equal to k, right? So this is cosine, cosine, right? Cosine, cosine. So if n and m are not equal, this integral is 0. Okay, 0. And also by the third one, sin nx and kx, this one, all right, no matter, this is 0 for all n and m. Not necessary to different. They can be the same. You can have the same n and same m. All right, so that you can see that this term contribute to 0. Okay, so the final thing would be AK and the cosine square kx and the dx cosine square. Okay. Yep. Because when n equal to k, so you have square. Thank you. Good question. And we have assumed that m is sufficiently large, right? But that's fine because we are taking the numerator. So that if m is sufficiently large, so m is greater than or equal to k, you have this term. Okay. Now you have the double angle theorem in trigonometry. The double angle theorem says that the cosine square kx is this one, right? So when you take the integral, you see that this is 0 because of 1. So you have a constant, okay? And so that this is equal to ak pi minus pi 1/2 and dx, okay? So finally, what you have is pi ak. Okay. So you have pi ak here. So now I have to erase the theorem, but I hope you still remember that. Right, so you know how to calculate AK. It's 1 over pi f of x cosine kx dx. All right, and similarly, okay, we can. So if we evaluate sine kx dx, and we find that this is equal to pi bk. Okay? And once again, this integral exists and is finite. Okay. So that bk is equal to 1 over pi of this function. Okay, so that a short conclusion. A necessary condition for a periodic function f with a period 2 pi to have to have a trigonometric series expansion f of x equal to a0 plus summation okay for almost all x in R such that the dominated function. Okay, I just stress that this function is indeed converges for almost all x in R and is integrable over this kind of interval from minus pi to pi. Okay, so the statement here is just that these two conditions are satisfied. Okay. All right, is that okay? So next one is that f is absolutely integrable. Okay, over minus pi and pi, and a0 is equal to, so a0 can be evaluated by this integral, and an and the Bn all right, so these three formulas are called Euler's formula. Sorry. All right, so they are called Euler's formulas here. So it's very important to know f is absolutely integrable. Okay, that guarantees that this integral exists and finite. Okay. Okay, and so an application of this next condition is that if a function, okay, if a function is not absolutely integrable, okay, if a function is not absolutely integrable, then it will have a high probability that, so if it is not absolutely integrable, then with very high possibility that we can't have a trigonometric series expansion for f of x. Okay. Now, so now we will use the this property, the absolute integrability of a periodic function. So now, so we will basically this property as a required property. Okay, we will regard them. Okay, as a property for a periodic function to have trigonometric series expansion. Okay. But you have to notice that this necessary condition is obtained with two additional properties here. We have dominated function. Okay, so we have implicitly to say that this dominated function converges for almost all x in R, okay, and integrable over this interval. Okay. But in practice, that they are satisfied, okay. Because the rare cases, rare cases for us to have a dominated function not satisfy these two properties. Okay, so that we have the. Okay, so the last before we leave the classroom, I will say that. So for a periodic function, f with a period 2 pi, okay, which is absolutely integrable, okay, over minus pi to pi. We can define a trigonometric series. A0 plus with A0, AMBN greater than 1 obtained by Euler's formulas. Okay. Okay, so that this trigonometric series will be called the trigonometric Fourier series, okay, generated by f. Okay, so once f is absolutely integrable, then we can evaluate those constants by Euler's formula, and use this constant to construct a trigonometric series. right? We can construct that. So it's the companion trigonometric series. This is our target. Okay, and then we have a very explicit target to show if this trigonometric series converge to f of x for all x in R, or for almost all x in R. So we have a specific target to go, right? Because at the beginning, we don't have a specific target to go. But now, when we know the periodic function is absolutely integrable, then we have a target. Okay, we have target. Okay, and so things makes it easier for us to follow. Okay, so I will continue this topic on Thursday. Okay, so that's it for today.